What did that smell? Maple syrup. Hello?
Hello, Chris.
Yeah, hello.
Hi, sorry for the delay. It was a bit complicated. Too many devices, but connected with the wrong one. So now it's correct. Okay. um, Today, Chris, we will do a couple of questions for the superposition of waves. And then most likely going to start on the stationary waves as well. That's not such a long chapter. Probably can do a couple of questions for the stationary waves as well, huh?
Uh,
Okay.
wait, can we skip to the questions because at school we already finished the waves chapter and we're doing the atomic things.
Ah, okay. So you would rather like to do the atomic stuff?
Maybe like skip to the the waves the questions.
Ah, well, okay, no problem. So anyway, so you mean so no stationary wave theory, huh? Just the questions as well.
Yeah.
Okay, all right, okay, we can do that then. But we do first the superposition of wave question. Is that okay?
Okay.
All right, okay. I mean that's okay, right? I mean, if you say I just would like to move on to the stationary direct, we can do that as well.
I want to try the superposition.
Okay, yeah, well, there's a couple of interesting. It's not so. Yeah, there's a couple of interesting questions actually, so we can do those. All right, good. Yeah, just tell me. That's fine. That's good. Um, then we start. Table. Okay. All right. Um, the one I would just like the last one actually from this type of questions. That was the number 15. No, because we have to rearrange a couple of things. Okay, we have white light. White light. And is normally incident for a diffraction. Huh? So incident normally on a diffraction in this case. And the slit separation D is 2 times 10 to the power minus 6. Huh? And the visible spectrum, okay, we know that, but nevertheless, we give that the range is from 400 nanometer, there's a bit, to 700. So, or sometimes we just check that ourselves. Huh? So what we want to calculate now is the angle. So it's diffracted, huh? With the split separation. And the white light is incident. And of course it will split. That's a bit the follow-up to what we've seen here in this one. And now we would like to look at the angles between the wavelengths. So and of course between, not of course, but between the red. I have to make the, sorry. Go to the fatter one. This is not really, sorry. So angle between red and violet, between red and violet for the first order. Huh? So how do we proceed with this question?
Um, so just uh, I think calculate the violet light first.
Okay.
So first is
Or just it's fine, Chris. Just a quick question. So when you say this first, so what is your overall intention? What is your overall plan to solve the question? Just quickly, verbal is fine. You just tell me.
because violet is the lesser angle.
Okay. All right. Okay. So yeah, and what will you do then? So will you need the red angle as well?
Yeah, yeah. Also needed.
Exactly. Okay. Yeah. I mean, I thought so, but just to make sure, so to speak. Okay. Violet. So how do we calculate the violet angle of the diffraction?
First use d sine theta equals
Mm-hmm.
400 times 10 to the power of negative 9.
Okay, yep. As I just wrote the general one. Okay.
1.
So d sine theta is say again please for the n times wavelength.
1 times 400 times 10 to the power of negative 3. Yeah, I mean negative 9.
Okay.
D is 2 times 10 to the power of negative 6.
Okay. Okay. Okay, so we get for sine. What do we get?
So 400 times 10 to the power of negative 9 divided by 2 times 10 to the power of negative 6 is
Mm-hmm.
so 4 times 10 to the power of negative 7 divided by 2 times 10 to the power of negative 6, and then I think it's just 4 over 2 times 10 to the power of negative 1, and then it's 0.2.
Okay, yep, okay, very good. All right, okay. So 0.2, and if you want, and that would be what unit of measurement? I mean, it's any dimension. And now what about the angle? Sorry, because it's not, it has no unit really. So it's diffraction.
11.5 degrees.
Okay, yep. All right, okay. What about the red one?
Everything is the same besides
Same,
the
right?
wavelength.
Okay, yep. That would be how much?
700 times 10 to the power of negative 9.
So 700 divided by 2, huh? So we get, when you look at that, I mean, I just jump ahead. When you look at that 700 divided by 2, what would that be? I mean, compared to the red one, if you take the same dimension.
350.
Okay, yep. And therefore, with the magnitudes.
So 350 times 10 to the power negative 3.
Yeah, huh? Okay.
0.35.
3.5, right. So you can make, you see, if you get 0.2 here, and we're talking about, well, red and also still visible light, right, which is in the range of the same magnitude, right? It's just either 4 times or 7 times. So henceforth, we can as well, so basically make, so at the moment we see 700 here, on the other end of the spectrum divided by 2, we can basically just jump directly to 0.35. But of course, I recommend not to do it, just to mention it, because it's always better to go through the motions, right, in order to have it. Sorry, that was long too early. And henceforth, what is the angle?
20.5 degrees.
20.5 degrees. So what is therefore the angle between the two?
It's 9 degrees.
9 degrees, huh? Okay. I mean, from a question point of view, of course, the last step is not really, I mean, of course, it's necessary from what is being asked, and that's why it's like that. But basically, it's like, okay, one is 20.5 and 11.5. But from a physical point of view, of course, because math-wise it's, well, trivial, obviously, makes a lot of sense to think about the angle between these two waves after the diffraction. And that is an interesting observation because that's what we're going to see as well. I mean, not just for obviously red and violet in that case, but when we do have diffraction for whatever situation, whatever type of wave in the end, could be from, say, outer space, microwaves, for example, from a planet, also not planet existing anymore, then of course that will tell us something then as well what's going on. Huh? So quite often we think of differential angles instead of the angle itself. Okay, that was that one. And then we can start with some more questions like here. And we can start with this one. I mean, that's just qualitative to explain. So we have a diffraction when with a given situation, given wavelength. Now, if the wavelength is increased, what's going to happen
There will be
with
less
the pattern?
diffraction. Less diffraction.
Okay. Also, yeah. How would you rather describe that in practical terms, so to speak, or visualize it? When you say like we have right now, we have them like this, then yeah, then they start to become a bit. They're still a bit more like that. So what happens with that pattern in terms of shape of the resulting ones? Or how could you say that?
It will be more like narrow and then less round.
With the wavelength increase. Obviously, we have the second question, right? When we decrease it, so the question is, what's the change of the wavelength increasing with everything else the same? Will the pattern become more rounded? Let's put it like that, or less rounded. So for question A, then obviously B is then just the opposite.
If it only increases by until it reaches the width of the opening, then it will be more
Yes, that's a
rounded.
good one. That's a good observation. Yeah, that's a good comment. There's a limitation. There's a question somewhere as well. We look at it today, which deals with exactly that situation, kind of. But assuming it's until the break off, so to speak, what happens to the wave pattern?
It will be more spread out.
More spread out, and hence we're more rounded.
Yeah.
Yeah, exactly. Okay, yeah, more rounded. So it's a good one. So more rounded, spread out. Oops, spread. And then obviously the other one is then just the opposite. Huh? That we reduce the wavelength, then of course, and how could you in practical terms explain that to somebody without going too much into details and formulas, just kind of a practical point? If you, what would you take into ratio to explain a bit what happens?
If the wavelength decreases, then it is less similar to the width of the opening.
Mm-hmm. Okay, yeah, exactly. So that ratio counts, right? So can it basically easily slide through? I mean, that's not really high physics, but it gives a bit an indication to people. That would be the idea here in that question, who don't really know much about it, to make it a bit more practical, tangible, and say, you know, if that wavelength is getting smaller and smaller compared to the slit, of course, imagine it just slides through, so it will not be disturbed. However, if you start to increase it, it will be more and more disturbed up to your very good point at the beginning, that it can't pass through anymore because it's too big comparatively to the slit, right? It just doesn't fit through, even if they don't really know about what really goes on with the wave in itself and the parameters, etc. This is a bit of a practical explanation, huh? Okay. Then the other ones, we can just go from here, the number 4. That is actually related to that one. So when we take remote mountainous region, well, it could be anywhere on planet Earth where we have high mountains, and could go to the Himalayas, for example, because that's really high up. But it doesn't have to be that high. It's enough if it's above couple 3,000 meters maybe. So Alps would be feasible as well. The question is, we have terrestrial transmitters, huh? So they are not up in the mountains, of course, in tendency. They are more somewhere. That's why maybe not too remote is a good idea, or depends on the wavelength, of course, if you really get them in the end. So we don't want to make it too complicated. Huh? So we just say there's a transmitter, we call it terrestrial, also sitting on the ground on Earth, not a satellite or whatever, and it sends out television, radio signals in the first place. And we say that when I want to receive those radio signals in the high mountains, I can receive them, but not television. What could be the explanation? So high mountains. So what will the mountains act like? What will be what we just looked at in the last lessons? What will the mountains be equal to, these high mountains?
Like a corner.
Okay, so exactly like corner, like what would be the magic word, so to speak? When we ultimately look at the phenomena, what happens to the waves?
Diffracted the waves.
Diffracted, yeah. So we look at diffraction actually. Yeah? So there we have a little bit of a practical example. So we have the high mountains, diffractions, and now we say that the radio waves come through, but the TV waves don't. So without knowing exactly the properties of the radio waves compared to the TV wave, but we know the high mountains act as diffractors. So what does that necessarily mean? Like when you say bending the corner. It's the diffraction may lead at first in the wrong direction, so I just have to. But that's why we say diffraction and not necessarily slit. Huh? That would not necessarily give us the right idea, probably. So like you say corner. Huh? So when you follow that one, how come? What must be the property of the radio wave so that it can be still reached up in the mountain?
It can bend.
It can bend, okay. And what does that mean in terms of, I mean, property of wave, right? We have basically two choices to talk about, even if it's the same in the end. Frequency or wavelength, of course, right? That's the typical property of the wave, first of all. So what would that mean now? Frequency we usually don't use in that context, right? Because we talk about a physical consequence of the length of the wave, so to speak. So what is the wavelength therefore?
Very long.
Very long, yeah. And henceforth, what means so very long, so long, very long. Huh? So big, with a big wave length. And what about therefore the TV? What must the TV be if it can't be reached there?
The TV can only accept shorter ones.
Exactly. It must be rather short. Huh? All right. Okay. So with a short wavelength, huh? In consequence. That means we can solve that question without knowing the property. We don't need the parameter, the data in order to say radio waves can be up to 1 kilometer, just as an information. 1 kilometer, whereas the TV signals. Also, well, nowadays is everything through cable, but assume we could send it through from, say, satellite. And we still have a wave, not just a digital signal, for example. So that could be centimeters or even millimeters. Huh? So centimeter or millimeter. And because the atmospheric situation changes throughout the day, ionosphere and anything else, so waves come through in not always in the same quality, and that's why TV screens in the past, well, that's really past now, used to have different antennas so that you could either catch the one with the signal X or the signal Y, so to speak. They were sending sometimes on different frequencies in order to have a better reach independent of the day. Of course, when that was in place, TV uh, was basically on from 6 o'clock in the evening, right? There was no 24 hours. But that has all obviously changed. So, but from a physical point of view, it's an interesting question. Huh? From a practical point, it stays gone. Even radio. Of course, you're very, let's say it like that, mountaineers, of course, are still very much relying on radio signals. Yes, there may be satellites stationed, geostationary ones, above, but maybe not. Depends a bit if you're really remote and there may be no signal from a satellite there. Then, of course, you cannot reach, which you would need a special phone. Well, it's in the end still like a mobile phone. It's just very different frequency and probably a bit bigger and has a larger antenna. As it has to, well, and it has to have a line of sight, right, with the satellite. That makes it a bit different too, compared to the mobile. And then, of course, you can be reached, but that is too insecure. So that's why typically mountaineers have, of course, radios with them with specific frequencies, specific frequency bands, as it's called. Again, it may be that they are comparatively close, then rather can utilize mid to shortwave kind of. Whereas if it's far away, a couple of kilometers, and to reach somebody, maybe a search troop, for example, to reach somebody who's lost, then of course they need the radio with a rather long wave. Huh? Okay, that's why we do it like that. Question 5. This is a interesting one. So we have a constant, we have a signal with a constant frequency. So a signal with frequency constant with a signal generator. So because we are doing experiments, of course, ultimately, if you listen to a radio connected to a loudspeaker, that's a signal generator as well. But now we want to focus on one frequency. And we have two loudspeakers. And we want to have nevertheless a stereo effect to measure. So they are 1.5 meters apart. And we have a student 0.8 meters in front of the loudspeakers and walks in the parallel line. So basically he goes from left to right at a constant distance to the loudspeakers. Left to right, right to left, that's not really the point here. Okay. And he measures, now that's an interesting point, the result of the experiment is he measures successive spots of loudness, so where it's really loudness, spots of loudness, they are 1.2 meters apart. Huh? So he walks in front of the loudspeakers at a certain distance. They are giving a constant signal, otherwise it would be difficult to make the experiment. And what we want to know now is the wavelength of the sound. Huh? So what type of problem are we facing here?
The constructive interference.
Okay. And what Hainsworth, what equation do we use for that problem? Or which parameters are in relation to what other parameter in which way?
We use the we use the distance apart to find the path difference and then the phase difference.
Okay. So when we think about like you said, constructive interference, right? So what is the path difference?
It should be equal to the multiple of the wavelength.
Okay, all right. So we can multiple of the wavelength. And what is that equal to? Also how would you express the path difference? Sorry. What is on the wave side, so to speak?
The path of each wave from the source to the point of where they meet, and then find the difference.
Okay. Let me see, just something I was. When we think of this constructive interference, which is correct observation, can we solve this question now with that approach, with the first basic approach? Or do we have to, I mean, we will not, how to say, we will apply ultimately some modified, which of course starts with what we just said. And it's actually that the reason for this question is as well that we utilize the one we usually link to another problem, but it's ultimately the one which is helpful to answer that question for the wavelength, because we have a couple of parameters involved, which makes it a bit more complicated than the straightforward constructive interference where we have the path difference, right? Or we have to, or in that question we would have to really modify that equation, extend it, actually expand it in order to answer the question. Because we have, when you think of it, we have the two loudspeakers at a certain distance to each other. So let's say the center here, that would be 1.5. We have the student, that's now not in proportion, which is 0.8 meters away here. So center to center, so to speak. .8 meters, and he's walking on this one, right? So he walks along here. And assuming he's starting at the front of one loudspeaker, then at 1.2 meters, he has a max. So that would be 1.2 meters, huh? 1.2 meters. So we have, it's a bit more from the geometric setup, right? It's a bit more than just what we typically have with the constructive interference. Of course, it's two loudspeakers. They generate the constructive interference, but in that one, we looked at it under the header of constructive interference with the multiple first, second, third max. Then we have a simple situation, right? Because we are talking stationary, that's why. Whereas here we are moving and then we identify the problem, but we take into account the distance as well.
So do we just calculate the like use just the Pythagorean theorem?
Okay, we could do that, but then we have to really spend a lot of time, which is a good point. That's what I mean by we would expand the basic equation and then come up with a solution. We can, on the other, which I would like to put aside so that we can know the questions, because what we can do here is utilize another equation, and what I want is when I tell you double slit equation, how could you eventually use that one? When you think of what is included there and how we would have then ultimately the analogy of what's happening here.
Oh.
Exactly. Right. That's why this is an interesting question, because if something like that comes in a test without previous preparation, most of the students will be lost, or like you, they will start with geometry most likely, but that is a long way, and then you lose a lot of time for the question. So that's why, of course, here the idea is to make this analogy. So, okay, yeah, please, Chris.
But do we know two points of the constructive interference, two adjacent points?
So we know that it's every 1.2 meter.
Oh.
Hmm.
Oh, then we can.
So we can utilize that one too. Yep.
So
Good
it's
question.
just it's just wavelength equals the 1.5 times 1.2 divided by
Okay.
0.8.
Exactly. In other words, when we label it and say we have the slit separation A, we take the fringe separation X, and we have the slit to screen distance. So we normalize the problem into this one. So slit separation, so make this one A. So we have slit separation, 1.5. We have the fringe separation, is 1.2, so that's the green one. And of course, we have the distance to the screen, which is the 0.8. Yeah, exactly. And then the problem becomes very simple, right? So there's this analogy that the two loudspeakers act actually like the slit separation, because basically well, if it would be without the cables and all, then we would have the situation that somewhere there's a source and the waves are coming, and then of course some of them will be like that and come here like this. So that's why we then get this a typical interference pattern. Okay. So that's one. So once you see that, of course, you will always see it. That's the good news. It's one of those problems. If you realize the analogy to the double slit problem. Okay, and how much would the wavelength now be?
2.25 meters.
Yes, 2.25 meters. Okay. 2.25 meters, or maybe something with less than meters.
225 centimeters.
Okay, all right. Okay. It would be less. That would be 2.25 meters. No, I'm thinking when you look at 1.5 times 1.2 divided by 0.8. Oh, wait a minute. Okay, let me see. 1.5. Also that's 1.5 is 0.1.8. Yeah, okay. Thank you. And we have that's okay, let me just cross check if I gave you the wrong information. I don't think so. No, it's all meters. Okay. Ah, okay, my bad. Okay, that's why I was. Well, it doesn't matter ultimately, for the sake, but it was 8 meters. Sorry, not 0.8 meters. Okay, huh? So that's why, of course, by factor 10. So we get 0.225, 0.225 meters. Huh? Okay, yeah. And the follow-up question would then be the frequency of the sound. So what is the frequency of the sound, assuming the usual 330 meters?
Then just 330 meters per second divided by 0.225 meters.
Okay. And that would be
1,467.
67 hertz. Huh? Okay. So even if you would have still had the distance differently, so we divide it by 0.8, then it would have been a feasible solution, right? Because we are still within the range of hearing by factor 10. But that's not a low range, that's already kind of mid-range with that signal. Huh? Okay, good. Okay, then we do question 7.
Wait, can I quickly go to the toilet first?
Yeah, sure, no problem.
Okay, I'm back.
Okay, great, no problem. And then we look at this one. Yeah, maybe nevertheless. I mean, it's not a very difficult one, but still. So we have hydrogen discharge lamp, also a hydrogen lamp. That gives us a bit of an idea when we again look, for example, into outer space or something like that. That probably could help us then at some point to identify which elements are maybe present in a planet, depending on such kind of signals, right? But this is just a side comment. So we have spectral lines. So we have spectral lines coming from the, and we have that hydrogen lamp. One, okay, well, we just take one of, obviously, otherwise too complicated, one of the spectral lines. And we take the one at 656 nanometers. 656, okay. 656 nanometers, huh? Wavelength. And the light is incident to a diffraction grating with diffraction grating. And it has 5,000 lines per centimeters. So what are the angles for the first and second order maxima? Huh? Maxima question mark.
I think first calculate the distance between the lines.
Okay.
So, 1 times 10 to the power of negative 2 divided by 5,000.
Okay. So you have, so this is, okay, so that's just for the separation of the slit, Chris?
Huh?
So what you calculate is, what did you just calculate, Chris?
The width of the lines. The
Okay.
width between the lines.
Okay. Okay, yeah, exactly, yeah. So, or you may say that as well, the separation of the slits, huh? Okay. Yeah, oh, okay. All right, and that's how much? Call that D, huh?
2 times 10 to power negative 6.
Okay, yep. It's a bit like the period, right? For example, when we and the frequency, the relationship, same thing, just the invert, right? If you have 5,000 slits per whatever centimeter, millimeter, meter, then the invert of that one, of course, is then just the distance. Okay. And now for the first one, when you want to calculate the maxima, so what is applicable here? Again, so to speak.
Using the d sine theta equals lambda n.
Mm-hmm. Okay. All right. Okay, so that's important. That always shows up again and again. In most cases, we usually, of course, like now, because usually, most likely, you always calculate the angle. So it always comes to the relationship between actually, when you look at it, right, in a more general way, then you can say, well, forget about the sine for the time being. Then you can say that the angle is proportional to the ratio of the wavelength to the D, to the slit. Which makes a lot of sense, actually, right, when you think of it. So this is like the simplified approach, because we talk about small angles anyway, usually. So, of course, theoretically, we can approximate the sine of the angle with the angle, because it's a small angle. Depends a bit really on how far we go. In this case, no, because the calculation results in in the first case with 19 degrees. I'm just jumping ahead. And in the second one with 41 degrees, of course, that's not on a small angle. But if it would be, say, between 0, also greater than 0, and maybe up to 10 in tendency, you could then say, well, the sine of the angle is basically equal to the angle itself. That is then something we sometimes see in simplification models as well when it comes to diffraction and waves stuff. Huh? Okay, so That's why this one is not too bad, because that's where we then as well can instantly answer the questions of the change of angle, right? When you say, okay, it's the ratio between the wavelength and the slit. If the slit stays the same, but the wavelength changes, of course, if it goes up, the angle goes up. If it goes down, the angle goes down. Quite simple, actually. And hence, we can instantly say what happens to the wave appearance or pattern. Huh? So we will not go into the calculation. This was just more about recalling that one. The calculations are, well, just straightforward, simple in the end. Huh? So, and maybe last but not least, now we do this one. So what we do have for that question is an experimental setup to analyze the spectrum of a sodium discharge lamp. Huh? So we take a sodium lamp. And would you maybe know what in tendency, what type of color the sodium lamp would have in tendency? Or would you know where they are used to be, and now it's changing as well, but used to typically apply or used these sodium discharge lamps?
I don't know.
Okay, that would be the street lamps. So when you see the slightly yellowish tint of the street lamps, that's because they are sodium discharge lamps. Huh? So that's why they're not white. But that has changed because sodium gives a slightly diffuse light. So that's for road traffic security safety, not the best. So they have been replaced. But before that was a good solution because they were long lasting. Energy-wise, quite not too bad either, compared to say neon tubes, right? They have to be changed all the time to some degree. So that was a better, more practical solution, actually. And that's just so the sodium discharge lamp. Of course, when we look at it, we have a spectre ultimately. When we make a diffraction, of course, we see what it's made of. And again, we make it 500 lines, the diffraction. Not again, but this time we make it 500 lines per millimeter. And we used a film, actually, in order to catch it. And you see that here in the display. Huh? Then we have a diffraction, the grating. And then we have the result as shown here. So, first question is, why can we see two spectra?
Because there's two regions where the constructive interference happens.
Okay. And okay, yep. And in order to let's assume that will give 2 marks. I have not listed it here, but what else would you have to explain as well? Because you see two specters, right? We have the wire. So what does that tell us? Then you think of the order of the waves. Or in terms of first order, second order. And also, you know, when we talk about, I mean, of course, there's a symmetrical here. So we have this pattern and we have that pattern, huh? Or two spectra, as it's called here, actually. So why does this one occur? What is the ultimate reason here why we have this type of appearance? What do you think, Chris?
Because the there are different wavelengths of light in the sodium lamp light.
Okay. And what does what so wavelength? How can you explain that when you have the sodium discharge lamp? When you see what you see, when you think of orders, what must happen?
It must be diffracted. Uh, like it must be diffracted in a very wide region.
Okay, yeah. Okay, yeah, okay. What you could say is, like, for example, what what does first order tell you, or second order? When you take the path difference and the wavelength into account. It has a very practical meaning, right? It sounds very complicated somehow, very sophisticated somehow too. First order of the maxima and stuff like that. But what is behind that? Something ultimately quite simple, right? Once you know it, of course, it's always the same. So it's not simple per se, of course. So don't get me wrong, please.
With the stream disconnecting.
Okay, yeah, that's the screen distance. Does that really matter here when we talk about the order? Or what is or when you look at the path difference, and I'm telling you it's of the first order, what can you tell me then what the path difference is? What is the path difference equal to in the first order?
Uh, one wavelength.
Yeah, exactly. Exactly. Huh?
Oh,
Yeah. Right. It's important that sometimes we gets a bit lost. I fully understand that. That's why it's actually really straightforward, simple, and say, hey, if I'm talking about the first order, it means the path difference is one wavelength. If I'm talking about second order, the path difference is two wavelengths. That's it.
oh,
Huh? Which makes a lot of sense. And then, of course, we need to know, which we do, a bit the background of the geometry and the longer path it has to take, which is obviously then time, like we discussed last time, time and distance, right? They are a continuum, so to speak. So it's a matter of how you split it. And when you look at a fixed position, which means it has a fixed distance, then of course the distance becomes either longer or shorter, depend like what we know, right? Depending on the diffraction, and henceforth, as the how many how much distance I can make within a certain time period, time becomes longer. And henceforth until it arrives, which is then equal to a different distance, meaning wavelength. So there's a bit of a link between that space time continuum actually, but we don't even have to go so far in our thinking. We just can say, okay, I mean, it's a longer path, same velocity, same speed. Let's call it speed. It's better. And henceforth, of course, well, that distance takes longer, which means ultimately they are further apart. It depends on how you look at it, huh? Is that okay so far, Chris?
yeah.
Okay. So that was the first question. And when you look at these two spectra, what can you say?
Wait, I cannot see the
Oh,
screen.
has it gone? Sorry, yeah, because it went to black. Yep. Also, screen save. Okay, sorry. Okay, here we go. All right. Okay. So we have the two spectra, right? At A and B. So the A and the B, so to speak. What is the difference when you look at also here, this spectra and this spectra? What can you say about major differences, or let's say two differences?
The second order is more dense.
Okay, all right. And well, that's a bit difficult to see here actually for the second observation. The idea, well, that's really difficult to say from that one. What could be said, but that the lines at end A are brighter at end, right? When you look at here, brighter than here, or both here actually, compared to these, they seem to be dimmer, huh? But it's a bit difficult to see. So for that, you would rather need a color picture actually in tendency. But it's an indicator. So you just have to follow your guts a bit and say, okay, what is the most obvious one? First one you said, of course. The second one is, well, that seems to be whiter, meaning probably brighter compared to this one, which is a bit duller, huh? And well, for that one, this is well just looking at some results and giving some proper feedback about what we see. That's sometimes very important for experiments, right? Just describe what you see, no more, no less. And of course, the third question is the green maximum near end A is at an angle of 19.5. Let's jot that down. At point A, green theta is 19.5 degrees. Now, what is the wavelength of that green wave? It's basically our old friend, so to speak. But how do we utilize that in this context?
So 10 to the power of negative 3 divided by 500 times sine 19.5 degrees equals 1 times the wavelength.
Okay, so okay, so wavelength. We have the. Did you? What about the sine? Did you?
Sine is just 19.5.
Okay. Yep. Okay. Sorry. Yep. And we just have well, depends on how we look at 500 times. So how many times power of 10, Chris?
If it's like that, then power of 3, positive 3.
Yeah, power of 3. Yeah, exactly. Very straightforward. Millimeter means a thousandth, right? Like centi is a hundred or 100 centi, milli, kilo. But the other way around then. So let's not pray. That's forget that. So okay, and then how much is the wavelength?
6.68 times 10 to the power negative 7 meters.
Okay, all right. Huh? Okay, when you see there's not so many variations of the formulas anyway. There's a very limited range of formulas to apply. The questions can vary a bit, but ultimately, and you see, it's either a more complicated setup like this one, or a more straightforward one, or we have to find the analogy for the loudspeakers that it's equal to a diffraction situation. See stuff like that. But once we have identified that, it comes always back to the very similar calculations, right? And henceforth, then from some point onwards, they become identical. It's then just a matter of, do we have to calculate the d, or the angle, or the wavelength? So that depends on the setup of the question, so to speak. But the core of what we need to use in order to answer it is coming back always basically to the two, the ones we know so well now. Huh? Either with the maxima, like what we just did, or the one before where we have the double slit diffraction equivalent, and we can use that one in order to calculate, even if it's with sound waves coming from a loudspeaker. Huh? Okay, enough of that. So I think that covers it very well. Stationary waves, you've covered the theory. So let's just jump ahead. Maybe as a quick recall, what is so typical about stationary waves, Chris?
They have nodes and antinodes.
Yep, and what does that mean?
Points of the wave that don't move and points of the wave where it oscillates at maximum displacement.
Exactly, huh? So something, and where are the nodes guaranteed? Or maybe rephrase the question, sorry. How can such a stationary wave even be occur? How can such a wave occur? What's behind that? Because otherwise we know waves are just waves, right? So they behave, we saw that phase difference, stuff like that. But what about the stationary waves? What is, of course, a starting condition so that you even have a stationary wave? When you think of a spring, for example.
So, like there's two sources of the wave, of progressive wave, and then they are the same wave with the same frequency and speed, and they superpose with no phase difference.
Okay, yeah. I mean, what you say is correct. That's what happens. The core, but what is the core? I mean, yes, they are. How does the second wave occur? How's the second wave being generated? When we talk about a stationary wave,
with like a reflection.
Yeah, exactly. No, that's the key point, right? It must be somewhere reflected in order to get that effect. It's like thrown back, right? Like an echo, so to speak. Of course, we don't use that word echo, but it gives us an idea and say, okay, I throw out the wave, it will hit a point and it comes back, and because it's the same wave traveling all the way again and again, then of course it comes back in the same way until we get the result we typically encounter. Huh? Of course, we can have what are the two typical situations you can encounter when we think of these where the waves originate or where they are, yeah, the overlapping starts to come. What type of situations can we encounter typically? Let's think of an organ, for example, or air tubes.
Like a flute.
Yeah, flute is a good one. Okay. So what is happening there? What is that the equivalent to if we make it an abstract setup, so to speak?
The
So let's say this is the flute. Huh? Oops, should have been straight. Sorry. Like that. Yep, super. So assuming this is the flute, right? Would you agree with me?
yeah.
Ah, sorry. This is silly. Okay, just down. And of course closed. Okay, so the flute. So what is typical here? I mean, it's very obvious, but nevertheless, please tell me what is so typical here with the flute, or what we have here.
The progressive wave that enters will reflect, and then it will form a stationary wave inside.
Okay, all right, okay. So we have something like probably let's make it something like that. Ah, yeah, that sorry, that always that auto shape is sometimes a bit annoying. Let's make it like this. That's easier. Something like that, huh? And of course, well, it's really difficult to make it with that automatic stuff. Sorry. You know what? I mean, let's make it the other way around first. That probably helps more. Say what we have is actually nothing else but the same, something like this. And of course, yeah, if it's too slow, it doesn't work. Okay, well, that's not really nice, but that's the basic idea. Something like that. Huh? So we get that pattern. So now I'm following with the tube, basically. So it's a very sketchy part, but that's the point, huh? So what do I have here? So obviously, what do I call this point here?
The node.
The node, huh? And what do I call these points at B?
Huh?
I mean, or let's say this one and this one. What are these points?
The antinode.
Antinode, huh? Exactly. So that means obviously we have another node here as well. Huh? So wherever they where they meet, so to speak, or where they equal, then we have a node, huh? That's important. And of course, there's an impact on the length, right? So again, it's a bit related to what we had before, but we don't talk about wavelength to slit. We talk about wavelength in terms of length of the tube, for example. And when I say, okay, can you tell me what is the wavelength here from node to antinode? With such a open with a semi-closed tube or one open end tube, one closed. What is the
0.75.
in relation to? Sorry, say again, Chris.
0.75.
Yeah, exactly. Huh? Okay, 3/4. Huh? So this is so that's of course we see then as well why again numeric sequences are so well liked because there's a pattern behind, right? Which we can see how they are formed. And we have a major difference. That's as we said, we want to make more questions. And when we talk about strings, what will their pattern be? So that we have both ends, not closed, obviously, but so when we have the length of the string, so this is the length of the string, like on a guitar, violin, whatever, then what will be the wavelength at, at the very beginning? What will be the what will be the wavelength compared to the string length, so the length of the string? at the very first occurrence. What is the most simple wave pattern, so to speak, we can imagine with two fixed points, Chris?
Uh, like if you generate the wave from like one end.
Yeah, right, that, right? Just like, so we say we have the string, we expand it, we plug it, like on a guitar, for example. And then, of course, what we have first is like this one. And of course, well, then the reflection or the like that. So not nice drawings, but that's the point. So the wavelength then will be how much in that situation?
Half.
Just look at the picture again. I know it's tempting, but it's not. What is it? I mean, depends on what we say. Okay, I know what you mean now. I wanted to say expressed in length of the string. Sorry, you were right. It just I want to have the answer in a different way. That's why.
Oh, two lengths.
Yeah, exactly. Yeah, it's completely correct what you said. I was just focusing more on the situation of compared to the length of the string. Huh? So yes, of course, you can say the length is equal to half the wavelength. It depends on look at it from the left side or from the right side of the coin. Huh? And what do we call that typically? What is the name for that? For that occurrence when you think of music now, the term. Would you know that?
Huh?
You know, when you have that situation that the wavelength is equal to twice the length of the string, that has a very specific term, and then it starts to continue, of course, as we well start to shorten the wavelength or increase the frequency, if you want to say so. But what would that first occurrence be called when you have the first stationary wave situation? It's a bit like first, second maxima, but it's a bit, of course, a different term. But it still plays with first, second, and third.
I don't
Would
know.
you know that, Chris? This is fine. So this is called the first harmonic. Huh? Have
Oh,
you heard that?
yeah.
Yeah. Okay, this is fine. So or sometimes it's called the fundamental. Or that's why then the related frequency is typically called F0, right? Because surprise, surprise. Of course, then we get the second harmonic, and what is then the second harmonic? How does it look like?
One wavelength.
Yeah, exactly. So we have one wave. That's important to remember inside the length of the string. Huh? So we have the yep, something like that. Huh? That's how it should be. Not quite well, but now let me do it again because we should go half. Yeah, along these lines. Okay. So we have a complete wave, in other words. So the wavelength is equal to 1L. That's why it's a second harmonic. So of course, and then of course it generates the stationary wave, which is then going the other way around. So and so on. So what we then have here is then of course we have then, in other words, we have 1 times this one, then we have 2 times that frequency. And the reason why we call that harmonic, it seems that we, as human beings at least, perceive that as very nice sound. So at that moment, a string with a certain diameter at a certain length is being plucked, and it generates that first standing wave within the length of the string. That obviously generates a nice sound, which we don't feel as scratchy, itchy, or whatever. And that is then called the first harmonic. Huh? So that's why we call that the classics. The classical music is comparatively mathematical, right? That it went then quite far at some point that some composers used tried to use mathematical models like what you have in front of here to make music, and maybe on purpose destroy the harmonics and have something in between. That then depends on the musical taste, if somebody still likes that or not. But that used to be, especially in the 20th century, some experiments, just as a side remark. So, and then you have the third harmonic and the fourth harmonic and so on. So obviously, then the wavelength is, let's take the third harmonic. What would be the third harmonic in such a situation of the wavelengths?
1.5.
Yep. 1.5 at the third harmonic. With strings, no?
Oh, the wavelength is 2/3.
Yeah, exactly. I mean, that's why what is usually helpful is just to think about, well, how many waves are occurring. So sometimes you have to expand it into the second length of the string, at least in your visual or mental vision, so to speak. And then you can see it instantly, right, of how it fits in and where it's always with the notes and the anti-notes accordingly. That's where you can get it. And then, of course, the point is, no surprise, it's then 3 times the frequency, the starting frequency, the fundamental frequency. So 1, 2, 3, 4, 5. Huh? So this is when you have a string, 2 ends. If you have only one end, that would be an organ with the pipes of different length and diameter and even material, etc. I just cut it short. The frequency there is actually different because it jumps. Huh? So it goes from F0, or the frequency, to 3F0 to 5F0. So that means for an open tube, we only have the first, the third, and the fifth harmonics, huh? Because that's now where we can make the link, like with the maxima. What is in front of it gives us the harmonic. No? So, in other words, with a closed end, like a string, we have 1, 2, 3, 4, 5. So whatever. It's like with the maxima. Of course, we see that as well. There's the link to the diffraction then, n times lambda, right? Kind of. Not exactly goes into the frequency this time. Then the link of the lambda is a different one. Whereas with the open-ended one, also one side open, then you only have the 1, 3, 5, and so on. Huh? And the wavelength accordingly, of course, is a different story as well, because there we can see that it will become 4L. That's the point. Need 2L, it's 4L, and then of course everything is then in line with that. So it's just 4L, and then of course it becomes well, it's a matter of how we want to look at it. It's 4 third L, and then it becomes 4 fifth L. So that is a repetitive pattern. It stays the same, but this one then shows, well, like here we could say 4 divided by 1, right? If you really want to look at the sequence. Huh? So we have a constant, and then we have the number sequence from 1, 3, 5, 7, 9, and so on. Whereas here we have the constant, and then it just increases for the frequency. And for the length, we have a different pattern. It starts to be 1, 2, so 2, my bad, 2L, so 2, then divided by then 1L, and then we have 2 third. So it just continues like it goes, divided by the harmonics actually, divided by the second harmonic. That's why we have L, so 2 divided by 2. So in other words, you could as well say for the closed one, you could just say 2 divided by 2. 2 divided by 1 2 divided by 1, same thing. Then we have 2 divided by 2. Then we have 2 divided by 3. And if I would have positioned it at the right position, excuse me, because there's the second one in between. So here is the first, here is the second, here is the third, here is the fourth, and here is the fifth. Huh? That's the first one. And let's use orange for the closed one. So we have, of course, F0, F2, F0, 3, F0. That goes without saying. This one is just not existing here. 5, F0. And for the wavelength, we have then, of course, L again. So it's always in relation to the length of the tube, or in this case of the string. And because it starts at 2, so of course we have 2 divided by 1. Then we have 2 divided by 2, 3 divided by 2. Sorry, 2 divided by 3, of course, because that stays constant. 2 divided by 3, 4. 2 divided by 4. And of course, 2 divided by 5. Huh? Okay, Chris?
Yeah.
So you see, this it's just the starting point are different. So in other words, obviously the wavelength is double, which like you said here, 4L divided by compared to 2L. And then of course it just continues accordingly. This one, we can show that there will be no harmonic at this one. It will not show, but here it will because it's on double-sided fixated. Huh? Okay. Because this is really the core of it all, and all the questions, they more or less deal with that. A bit like what we saw before with the two equations, double slit and then the maximal multiple. So let's just do one question here and say we have x and x and x and y, and we have okay, that is of course should be like that, huh? So my bad. Okay, and we have on the other hand, of course, the opposite, that we go like this, like that, like this. And yep, here at the end. Go like this and then like that, and a bit higher up. Okay, so sorry for the lousy drawing. And make it a bit better here as well. Okay. So now, what we say here is we have 78 centimeters in between from x to y. That's 78 centimeters. And we have 120 hertz that the string is vibrating. F, whatever F that is. So we want to know the speed of the progressive wave.
Uh, 78 times 10 to the power -2 divided by 2. Then times 120.
Okay. And that's how much?
46.8 meters per second.
Yeah, okay. So what was the point here, the critical point to figure that one out?
the number of waves.
Yeah, exactly, right. To say, or in other words, the wavelength, right? Because you had the frequency, you know, and Ainsworth, you needed to have the accordingly to when you have the wavelengths, then of course together with the given frequency, you got the velocity or the speed of the wave. Huh? So it always plays with that. So sometimes we have to visualize it. Otherwise, we could not say. Maybe they would just give us a point and say, okay, a certain order. Obviously, how many fixation points does that way that have, Chris? When we look at that situation, what situation does that reflect here? That wave?
Like, is this moving in opposite direction?
Ah, yes, of course. Sorry, yeah, it would, of course, yeah. I forgot to say that because it's within the stationary waves problem.
Oh, then it's just a stationary wave.
Yes, exactly right. And the point is then as well that we say, well, it's fixated at two ends, right? So we don't have an open end. Could be it's probably a string, most likely, on one side, and we can see the right. That's the wave. So if we now say, if we would say, well, that would be very long, of course. Huh? So, but if we say the instruments L is 78 centimeters, for example, what can we tell then about the harmonics?
Uh, 4, like fourth harmonic.
So we have this is one wavelength, no? And this is the length, no? Exactly. So if it would be here, then which I mean it's absolutely right. So if it would be here, if that would be the length of the string, what would that reflect? Then what would that be?
Just first harmonic.
Yeah, exactly. Yeah. And if it's like this,
Then it's second.
exactly right. So what I want to say is it's very visual. So counting the peaks gives you actually the harmonics as well. So that's a good, well, an interesting aspect. Huh? Okay. What I will do, Chris, I will send you a couple of questions so you can do a bit of more exercise because we could, one part, yep, we could do that, but not the stationary waves so that you at least, if you have the time, can do a bit more stationary waves. Now, for next time, Chris, would you like to have some more or would you like to go into the atomic structure questions?
Atomic structure.
Okay, all right, okay. And just asking, how far have you gone there?
We only just started.
Okay, all right, okay, all right. That's good to know. Okay, right. Then thank you, Chris. And again, I will send you some questions for the stationary waves. And then see you next Friday. Huh?
All right. See you. Thank you.
See you. Thanks. Bye.